So hey there, welcome back to another video of Monotech YouTube channel. And in this video, I'll be talking about the applications of reinforcement learning. Some prominent projects use deep reinforcement learning in games with results that are far beyond what is humanly possible. Deep RN, which is reinforcement learning techniques, have demonstrated their ability to tackle a wide range of problems that were previously unsolved. Deep RL, which is deep reinforcement learning, has achieved human level or superhuman performance for many two-player or even multiplayer games. Such achievements with popular games are significant because they show the potential of the machine learning and AI models, reinforcement learning in a variety of complex and diverse tasks that are based on high dimensional inputs. With games, we have good or even perfect simulators and can easily generate unlimited data. Atari 2600 games machines achieved a superhuman level performance in playing Atari games. Go mastering the game of Go with the deep neural networks. Poker AI is able to beat professional poker players in the game of Heads Up, No Limit, Texas Hold'em. Quake 3, an agent achieved human level performance in 3D multiplayer first person video game, usually only pixels and game points as input. The Dota 2 NAI agent learned to play Dota 2 by playing over 10,000 years of games against itself. Open AI 5 StarCraft 2 agent was able to learn how to play StarCraft 2 a 99% win rate, usually using only 1.08 hours on a single commercial machine. Those achievements set the basics for the development of real-world deep reinforcement learning applications. The first one is robot control. Robotics is a classical application area for reinforcement learning. Robust adversarial reinforcement learning RARL is applied as an agent operates in the presence of a destabilizing adversary that applies a disturbance focuses on the forces to the system. The machine is trained to learn an optimal destabilization policy. AI powered rules. Robots have a wide range of applications, for example, in manufacturing, supply chain, automation, healthcare, and many more. Self-driving cars deep reinforcement learning is prominently used with autonomous driving. Autonomous driving scenarios involve interacting agents and require negotiation and dynamic decision making, which suits reinforcement learning. Next one is healthcare in the medical field. Artificial intelligence AI has enabled the development of advanced intelligent systems able to learn about clinical treatments, provide clinical decision support, and discover new medical knowledge from the huge amount of data collected. Reinforcement learning enabled advances such as personalized medicine that is used to systematically optimize patient health care, in particular for chronic conditions and cancers, using individual patient or patient information. Other in terms of applications, many areas are likely to be impacted by the possibilities brought by deeper reinforcement learning, such as finance, business management, marketing, resource management, education, smart grids, transportation, skin science, engineering, or art. In fact, deep RL systems are already in production environments. For example, Facebook uses deep reinforcement learning for pushing notifications and for faster video learning. With smart prefetching challenges of deep reinforcement learning, multiple challenges arise in applying deep reinforcement learning algorithms. In general, it is difficult to explore the environment efficiently or to generalize good behavior in a slightly different context. Therefore, multiple algorithms have been proposed for the deep reinforcement learning framework, depending on a variety of settings of the sequential decision making tasks. Many challenges appear when moving from a simulated setting to solving real world problems, limited freedom of the agent. In practice, even in the case where the mask is well defined with explicit reward functions, the fundamental difficulty lies in the fact that it is often not possible to let the agent interact freely and sufficiently in the actual environment due to safety, cost, or time constraints. A reality gap. There may be situations where the agent is not able to interact with the rule environment but only with an inaccurate simulation of it. The reality gap describes the difference between the learning simulation and the effective real world domain. The next one is limited observations. For some cases, the acquisition of new observations may not be possible anymore.